All right, welcome back, ladies and gentlemen. In this video, we are going to continue another example of parameterizing a line, or finding a parameterization of a line through a set of points. And we are also going to find out how to find the parametric equations for a line segment. So I'm kind of going to combine these into one video because I'm going to use the same points on the same line from example 5 into example 6 as well. So in the previous video, we defined what a vector equation was. A vector equation was just simply a position vector plus a direction vector, and that direction vector, of course, could be multiplied by a parameter or a scalar to kind of determine how far across the line we are taking that next point. And so for this example, I want to kind of do another follow-up to the previous video. So if you haven't watched that, I would definitely watch that guy first. And then we're going to dive on into finding the parameterization of the line through the following points here. So let's go ahead, and I want to draw some context first and foremost. So draw a little graph, and just to kind of show everybody the kind of, I guess, where we currently are in the example. We've got point -2, 3, and point 1, 2, 3, 4, 5, 6, 0.36. And so here we have our points A and B. And so if we kind of think back, I guess, for a sec as to what do we want to call the direction, or excuse me, the vector equation to get things going first and foremost. Remember, we need the position vector and we need the direction vector. And so let's go ahead and just call it something for right now. I don't see any V's on the screen or anything right now. I personally just like to use V for vector. I know a lot of people use R. Honestly, it doesn't matter. Whatever you want to call it, it's arbitrary at this point in time here. And so I'm going to kind of just draw a line through. I'm going to make it dotted through these 2 points, just so we can kind of see what vectors and everything that we're going to be talking about here. So what I need is a position vector, and I'm going to have to add that to some kind of direction vector, which is multiplied by some scalar or some parameter that we are going to be discussing. And so let's take a look at what we can say for our position vector. Well, the position vector is going to start at the initial point, and, or excuse me, it's going to start at the origin, and it's going to take us to that initial point A. And so I'm going to draw on here on the screen, I'm going to draw a initial position vector for us. We'll keep it in purple. So if we're at the origin, I'll call that point O, so I can have my position vector at OA. And so that means we know that the vector will have a position vector at OA. So now you've kind of set the position, and now from this point your direction is saying, okay, well, if I'm at A, how do I then go towards B, right? That tells us the direction in which we're going to be moving on this vector, if you will. And so we want to go ahead and find out what that direction vector is going to end up producing. So now I'm going to go ahead and change colors here and just kind of show what do we want to see. I want to see the position vector from A to B. And I'm going to have that position vector being multiplied by a parameter, just because, well, now AB is the direction, but what if there was a random point out here? Maybe it's P, or maybe there's another random point out here, we'll call it Z. Any of those random points that could be out there, that parameter is going to kind of tell us, I guess, if you will, how do you get to those points specifically. So let's go ahead and find out what the values of these vectors actually are going to be. So our vector, our OA, is going to be at -2, 3. All right, and again, just because -2 minus 0 is going to be -2, and 3 minus 0 is going to be at 3. So then we're going to add that to our position vector, which is going to be, our direction vector, which is going to be at AB. So the distance from the x component at -2 to our x component on B, 3, you're going to have, excuse me, x2 minus x1. So we have 3 minus a negative 2 for a total distance of 5. Now I'm going to write that out all the way at 3 minus a negative 2 just so you can see all of the numbers that I'm using here. And then for that y component, that's going to be the y2 minus the y1. So you're going to have your 6 minus 3. And that's all still being multiplied by our parameter of t. So that means that our vector that we're talking about here, our vector equation, is going to be at negative 2, 3. And then 3 minus a negative 2 is 5. And then 6 minus 3 is 3. And that's being multiplied by our parameter of t. And so ultimately, this vector can be written as the component of x comma y. Now, at this point in time, I really am adding two vectors together. So I am adding my two x components together. So I'm going to say that it's negative 2 plus, now careful, please don't call this negative 2 plus 5 and make it 3. It is negative 2 plus 5t because you had that scalar being distributed inside. And then same concept for our y component. We are going to take 3 and add it to the 3t component. So 3 plus 3t. And so that would be your vector equation. And if you truly want to parameterize the line and get the parametric equations that go with it, you can just separate it and call it x equals negative 2 plus 5t and y equals 3 plus 3t there. And again, I mean, it'd be wise to kind of give some ideas for the parameter. I mean, in this case here, it's a line, so it's going to go for all real numbers. So that is our parameterization of a line. Now let's go ahead and use that same example and just find a specific segment that we are going to be discussing. So I guess when the concept doesn't change a whole lot when you are talking about a specific line segment that we're going to be looking at here. So what I want to kind of just look at first and foremost is, are there restrictions on anything? And it says find a parameterization of the line segment with endpoints A being at the same point, negative 2, 3, and B being at the point 3, 6. And so in the previous equation, or previous example, we already found the parametric equations to be x equals negative 2 plus 5t and y to be 3 plus 3t in this case here. And so if you kind of think, I guess, of what ends up happening when you have, right, the restricted domain, if you will, from when it will create the point B. So here's what I mean by that. If you sit there and let t equal 1, right? If you let t equal 1, you are going to end up producing this point B, right? So if you substitute 1 right on in, you end up getting that x equals positive 3. You substitute 1 right in, to our y, and you get that our y value is a positive 6. And so you get that actual domain of it. And so we can sit there and say, for example, that we will parameterize this segment from x equals negative 2 plus 5t and y equals 3 plus 3t from 0 to t, or from t is from 0 to 1, excuse me. And the reason why that 0 comes on into play is because, well, what would happen if you substituted 0? Well, if you substitute 0 on in, if you let t equal 0, you're going to end up getting your a coordinate. And so you will end up seeing that that x would equal a negative 2, and then y is going to equal a positive 3. And so we're going to parameterize that for all of the values that lie in between 0 and 1, if I'm just getting it, right, from 0 on.